Hello everyone, welcome back. Today we are tackling a classic hard lead code problem, and that's a favorite at companies like Google, Facebook and Amazon. Problem number 297, Serialize and Deserialize binary tree. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we have to design an algorithm to serialize and deserialize a binary tree. And what does that even mean? Let's break it down. Imagine that you have built this binary tree in a program and it is sitting there in your memory with nodes and pointers connecting everything. Now, what if we want to save this exact tree to a file or send it over the network to another computer? You can't just save this memory address of the root nodes, as that address won't make sense anywhere else. It only makes sense on your computer. And this is where serialization comes in. It is the process of converting a data structure or object, in this case tree, into a sequence of bits, for example like a string, that can be easily stored in a file or a memory buffer or transmitted across the network connection. And then you need a way to reverse the process. And this is deserialization. In deserialization, we are taking that string and rebuilding the exact same binary tree from it, node by node, pointer by pointer. So first we design the serialize function, which takes the root of this tree and turns it into a string. For example, it might produce a string like this. And then the deserialize function takes the string and perfectly reconstructs the original tree. And this problem gives us a lot of freedom. It says we don't have to follow the Leetcode specific format. As long as our serialization and deserialization functions work together, we are good to go. Now let's see how we can solve this problem. One way can be, during the serialization, we preserve the in-order traversal along with the pre or post-order traversal. We can store these strings separated by some delimiter, say hash. And then for deserialization, we would just split the string to retrieve the preorder and in-order traversal. And from there, we can use the standard algorithm to reconstruct the tree based on those two traversals. We have already covered this problem where we built tree with in-order and preorder traversal. If you are interested, please check out the problem in the I button or description. Now this looks like a good code reuse, but during the interview setting, it will be a lot of work. So let's ask a better question. Can we do this with only one traversal? And the answer is yes. Let's try it out. Since it's a tree problem, we can use simple top-down traversal, and both breadth-first search and depth-first search can help us here. But we'll focus on a preorder DFS traversal because it leads to a very elegant recursive solution. In preorder traversal, we process the parent, then the left subtree, and then the right subtree. For example, here we start with the root node 1 and say during the serialization, we append it to the string, and then we go to its left child and append it to the string as well. But we should use some delimiter like comma to separate the nodes, and later during the deserialization, we can split the string by this delimiter or separator and use the resulting values to rebuild the tree in the same preorder sequence. And now we are done with the left subtree and we go to the right subtree. But if we just do a simple preorder traversal and save the numbers, we will get the list like this. And looking at this list, we have no idea what the tree's shape was. For example, just by looking at the sequence 1, 2, we don't know if 2 is the left child of 1 or the right child. And this is the core problem. A simple traversal, whether it is in order or preorder, loses all the crucial information about the tree structure. And this is where null children can help us. For instance, if we store nulls in the string for the null nodes, then we know for the string that 2 is the left child of 1. However, if the list was like following, then the left child of 1 is null. So 2 must be the right child. So in summary, if we want to preserve the tree structure, we must also preserve its emptiness. And we'll do this by explicitly recording the null nodes. As we traverse through the tree, whenever we hit a null child, we'll add a special character like a hash to our string. And in a way, it is like giving the directions. You don't just say which roads to take. You also have to sometimes say this road is a dead end. And our null markers act as those dead ends, telling us exactly where the branches of the tree stop. So now in the left subtree, we won't stop after node 2, but we go to its children, which are both null. First we go to the left and append hash to the list for the left child. And similarly, we do the same thing for the right child as well. And now we are done with the left subtree. So we backtrack to 1 and go to the right to node 3 and append it to the string. And then go left to node 4 and append it to the string as well. And then node 4's children are null. So we append 2 hashes to the string and backtrack to node 3 and go right to node 5 and append it to the string. And then node 5's children are null. So we append 2 hashes to the string. And now we have processed all the nodes. So we are done and this is our final string. It beautifully captures the entire structure in a single string. Now let's look at how the deserialization will work, where we will use this serialized string as a stream of data to rebuild the string. First, we will split the string by the delimiter, which is comma in our case, to get a list of values. And to easily process this array like a stream, we can put it into a queue. While we could have used it as a list or an array, we'd have to manually pass in the index around to keep track of the position of the value. So using queue is simpler because it handles that for us. And now using this queue, we can build this tree recursively, again following the preorder pattern, that is going from node then to the left child and then to the right child, which is what we use to create the string during serialization. And here is how the recursion will work. First, we poll the next value from the front of the queue. And if the value is our null marker hash, then this branch is a dead end. So we return null. But if it is not hash, then it must be some number. So we create a tree node from it. For example, here we will create node 1. And now because we are following the preorder rule, after building the node, we know that the very next values in the queue belong to the left subtree. So we make a recursive call to build the left child of our new node. And after the entire left subtree is built, we know the next values in the queue must be for the right subtree. So we make another recursive call to build the right child. So let's go to the left where we pop out value 2. So we will create node 2 as the left child of node 1 and go to left of node 2 and pull out the next value from the queue, which is hash, which will result in a null node. And here we have hit the dead end. So we backtrack and come to node 2 and go to its right where we pull out next element from the queue, which is hash again. So we add right child as null. And now node 2 is fully constructed. So we should backtrack and come to node 1 and now try to build its right child where we pull out next value is 3. So we create a new node from it and set it as a right child of node 1 and recurse deeper and pull out node 4 from the queue and create a new node from it and set it as a left child of node 3. Then the next two values pulled from the queue are hashes. So these values become null left and right children of node 4. And now node 4 is complete. So we backtrack, come to node 3 and go to its right and pull out the next value from the queue, which is 5. So we create a new node from it and set it as a right child of node 3, and final two values we pull out from the queue are hashes as well. So these become null left and right childs of node 5. And now node 5 is complete as well. And now we have built the entire tree because we have processed all the values in the queue and now our queue is empty. So this is how we will reconstruct the tree from the incoming stream. Now the time complexity of both serialize and deserialize is O of n, because during the preorder traversal we visit each node and each null marker exactly once, and space complexity for serialize will be O of n, because we need space to store the output string, which is proportional to the number of nodes and nulls in the input tree. And then for the deserialize, we are storing the splitted string values in the queue or a list, which again takes O of n space. Also, we are using recursion stacks in both serialize and deserialize methods, again taking O of h space, which in the worst case of a skewed or unbalanced binary tree will be O of n. That's why the overall space complexity of serialization and deserialization functions is O of n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, let's look at the serialize function. Here, we initialize an empty list that will hold the node values along with the null markers in the preorder. We then call the recursive function build list to build this list. And after the traversal is complete, we simply join the elements in our list with a comma to form the final serialized string. Now let's look at the build list function. Here, first we check for the base case, which is if the node we are looking at is null, we simply add our special marker hash to the list and return. This is how we mark the emptiness. And if the node is not null, then first thing we do is to process it by adding its value to the list, and then we make a recursive call for the node's left child, and after the entire left subtree is processed, we make a recursive call for the node's right child, and this completes the walkthrough of the preorder traversal. Now let's look at the deserialize function. In the deserialize function, we first do a sanity check, which is if the input string is empty or null, we just return the null, denoting the empty tree. Otherwise, we split the string by commas and load the resulting values in a queue. A queue is the perfect data structure here because we need to process the node values in the exact order we saved them, which is first in, first out. Now we call the recursive helper function, which is build tree, to construct the tree. And first thing we do is pull out the value from the queue. If it is equal to null marker hash, it means we have reached the dead end in the tree structure. So we simply return null. But if the value is a number, we create a tree node from it and do the magic by making a recursive call to the left to create the left child for our new node. And our function will go all the way down the left path, building the entire left subtree before the next line of code is ever reached. And once the build tree call for the left tree finally returns, we do the exact same thing for the right child, making another recursive call to build the entire right subtree. And finally, with its left and right children fully constructed, we return the node we created. And this completes the helper function for deserialization. So, while the core logic is on the simpler side for the hard problem, the real difficulty is in the implementation. Coding both the functions serialize and deserialize perfectly under pressure without missing any edge cases is what makes this a true challenge. I highly recommend pulling this up on Leetcode and try to solve these problems in a timed session. See if you can code this full solution in under 30 minutes. It is the best way to build the speed and confidence you'll need for a real interview. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.